Quantum Unspeakables, Conference in Commemoration of John Stuart Bell. The conference took place from the 10th to the 14th of November 2000 at the University of Vienna. The registration and welcome party took place at the International Erwin Schrödinger Institute.
Excuse me, I should mention that for those who have not registered yet, the registration desk is at the end of this hall. Please drop in, okay, if you can. It doesn't cost anything, it doesn't hurt. I have registered. You haven't registered. You could have tell him apart. No. There should be signs.
Ladies and gentlemen, welcome to the Erwin Schrödinger Institute. We are very happy to greet you here, the participants of this conference. Many of you are also participants of the currently going on program on quantum information theory and computation here at the Institute, and they will, also you will know the premises here.
So please go ahead and use the food, whatever is left here.
Yes.
And see you tomorrow at 9 o'clock at the meeting.
Yes. Right.
Words that should be forbidden in serious discussion: system, apparatus, microscopic, macroscopic, reversible, irreversible, observable, measurement, for all practical purposes. Note by John Bell.
In my opinion, the situation which is revealed or concealed by quantum mechanics is a strange one that we have not really digested. Most theoretical physicists don't worry about this. It's a little bit like riding a bicycle. You know, you can ride a bicycle without knowing very much how it's done and without being able to tell anybody else how to do it. And I think that most theoretical physicists use quantum mechanics rather in the same way as they ride a bicycle. And if you stop to think what it really means, then you get into problems and you can spend a lot of time on those problems.
Apparently, I'm the only speaker at this conference who was born after Bell's theory. So I think being able to talk here, which is probably due to the organization by my two advisors for signing us. And I also have the privilege to talk about some of the latest work related to Bell's theorem on the experimental side, paired together with the work by the Geneva group. We did the most advanced experiments towards Bell's inequality. And furthermore, I will also give you a short introduction to our latest piece on entanglement research, which is an experiment on the GH-Z theorem, or GH-Z correlation.
And it is true that in that time, for instance, in my country, it was not fashionable at all to work on this kind of subject. Foundation of quantum mechanics. Come on, foundation of quantum mechanics in 75 or in 70, everybody knows that quantum mechanics is working. And what I found is that the best way to reply to these people was just to explain Bell's theorem in the most naive way. All the predictions of quantum mechanics is a red line, and my very simple model is a green line here. And it fits quite well for a first try. And so, you can ask, can I, with a more sophisticated model, using this kind of special function that theoreticians like, Bessel or whatever, modified Bessel, Hankel, etc., probably I will be able to do that. Can I do it? And then we have Bell's theorem that tells us the answer. And Bell's theorem is a very short theorem. There is no way you can put the green line on the red line. No way.
One of the first encounters I had with John Bell, which really had a complete change, or induced a complete change in my life, had a tremendous impact on me. That was when I was a very young postdoc, just finished my PhD. And my supervisor was organizing a winter school on foundations of quantum mechanics in Switzerland. That happened in the basement of the hotel, something where the ceiling was like that. We just modeled in a overhead projector sitting on the floor, and John started, and I remember very well the first sentence. It started, "I'm a quantum engineer. I just finished my PhD in critical physics. This was the master, and he was presenting himself as an engineer. I was already shocked, but he continued. But on Sundays, I have concerns.
And we designed the whole experiment, and except for one thing, the dissociation part, we didn't get done at a point which Stefan went to work for John Fowler at Berkeley. And after he had left, I was continuing on and discovered that actually dissociate silver diamonds required lasers of such high power that it made the experiment useless. And I was really down and started looking around, and I started going to the periodic table looking for ways to do this. And came up Mercury. And so that's the experiment I'm going to tell you about. And actually, later on in the game, Thomas Walter came to work with me.
The question is, why did John Bell discover Bell's theorem and no one else did? It's not a hard theorem to prove. Once the theorem is stated, what sort of question is asked? Well, he had great intellect. There's just no doubt about it. But it's a very easy theorem. People, given the question, people with much smaller intellect answer, which I don't think is sufficient. There is also an intellectual content of posing good questions, and sometimes that takes greater intellectual ability than solving, and that he had also.
And this brings me to the second reason why my interaction with Bell was for me so important. It is that this proof of a deeply ingrained concept points, in fact, in a direction quite consonant with my own line of thought. In a way, it brings us up to Descartes. So, as we all know, Descartes was the first scientist who dared questioning our common views, including even the notions that have always seemed so primitive and obvious that thinkers, scientists, and so on never hesitated in making use of them.
I have to admit that I was never very good in my memory, and as an old man, I have not gotten better. My memory is almost non-existent, so it will be very strong. I had the opportunity to get to know John starting the beginning of 1965 and sort of through the 60s. I had a good chance to, I can't say work with him because we not work together, but to benefit from his understanding of things. And that was just after CP violation was discovered in the middle of 1964. I came to CERN to do an experiment on CP violation, which lasted for about a year and a half after that, and gave me the chance to learn from John. We were totally unaware of Bell's contributions to the fundamental understanding of quantum mechanics, which he never mentioned, and I was totally unaware. I'm sorry that I know so little about John. I had the privilege of being with him for some time. I appreciate him a great deal, but I can't offer you more. Thank you very much.
Let me then first look at this case of linear acceleration. So let us assume that we have, let's call it a point detector that is has a constant acceleration in its inertial rest frame, constant proof acceleration. That means it follows a hyperbolic path in space-time, the blue line here. And to this certain detector, we can associate a cold moving frame. And this frame, in fact, can be extended to a full coordinate system that covers part of space-time. That is what we call the visual coordinate system.
John and I were interested on that problem. In fact, it turned out that at that time also there were a couple of papers of people claiming that it was possible to give rigorous upper bounds on the contribution of hadronic vacuum polarization to the G-2. John looked at those papers and very quickly he realized that those bounds were not rigorous at all. There was no bound. And that was the way that we started getting to work together. I want to tell you a little bit what we did. And then I will try to build on how physics works, this kind of learning.
So what this is meant to illustrate is the range of contexts in which the original axial anomaly that John Bell and I discussed, the range of contexts in which that anomaly plays. Not only is it relevant for particle physics, not only does it resonate in mathematics, but also in classical physics subjects, like fluid mechanics or magnetohydrodynamics. It or its descendants have a significant role. Thank you.
I returned to CERN a couple of times, had the pleasure of meeting Mary and enjoying the hospitality. In this process, we also had a collaboration going, which resulted in a couple of papers on the problem of understanding the quantum status of fractionalism. During this interaction, I developed, like so many others before me and after me, great awe and respect for John Bell, not only for his originality and prowess as a theoretical physicist, but equally for the precision of thought and language that he demanded of himself and of those who were working with him. As was mentioned very beautifully by the first speaker in this conference, John Bell was more than an intellectual force.
But really, it's going to be a talk about my interaction with John Bell. Basically, in the period 65 to 67, I had a lot of interaction afterwards, but I think this is perhaps the more specific and interesting period. So I've broken this up into a number of items. Of course, the really interesting thing that came out of it was what Roman described on Friday. And this is all the kind of sociology or history of the subject, basically.
What are the magic moments? One of the habits of John was that at 4 o'clock he had to have tea. So 2 minutes to 4, we stepped down to the Sun restaurant, and John went to the bar.
And I should do that in 1 minute?
The similar ritual also happened when we worked at his home.
For me, it is just fascinating that the world is connected up in a much more intricate way than classical physicists thought, and even than most quantum physicists think, because mostly they don't think about it. Do you prefer a short answer, or I give a lecture? It's as you wish.
I recall my collaboration with John and the time we spent together. I really can say it was magic moments, and I hope that I could give you a little impression.
In this talk, I'm going to discuss a theorem
group by John Conway and myself, which I believe throws new light on the old 1960s results that are now called Bell's inequalities and the ocean-effect paradox or theorem. The original results were essentially negative in character, showing in different ways that quantum mechanics differ sufficiently radically from classical mechanics so as not to admit hidden variables, at least of a certain kind. And thus these results said what quantum mechanics is not. The new result is a positive one, allowing one in effect to
The purpose of this talk is to try to consider this question in view of the recent approach to physics based on information. The information concept has now been grafted in most fields of physics. And of course this is partly due to the fact that it has its commercial value. People can get funded by mentioning information application. But of course in this meeting, we should really try to look at things from the basic physical point of view.
Let me tell you about the only incident that I had with John Bell. I met him once, and that was in 1988, in March of 1988, at a gathering at UCLA in honor of Julian Stringer's 70th birthday. It was a kind of depressed audience because Dick Feynman had just died a few weeks ago. And so the meeting was actually rededicated to the memory of Dick Feynman. But anyway, they had invited distinguished speakers, which included John Bell, Gerard Toft, Nambu, Shelley Glashow.
Oh, by the way, I looked in the basement to see if I could find my actual scrap of paper with those functions. You know, if I could actually find my original model. You know, went through moldy file cabinets down in the basement. And I found a folder that said explicit hidden variable models 1968, but it was empty. But I mean, everybody, the correlation is weak. It's poorer than 1/2. It's 1 over 2.08, according to those quantum functions. And so the model is pretty straightforward to build. It's closely related to the Fermi model that they're on at the moment. And you get everything.
It's something seems to bear out that you can stop from very little.
Krems. This is Krems. It is the second biggest city of lower.
You see the sign here? This goes to the place where they found the Venus. This is the figure which became famous because we used it in our quantum cryptography. Well, never mind. We go.
Some work. But otherwise, let's see. It's too cold outside. Then you recover.
Of monastic life in the Western world. In about 45 minutes, we will come up the imperial staircase, and in the prelacy, we will see the most precious objects we have here in Melk, the monstrance of St. Coloman and the Melk cross. And then we will see the marble hall, the balcony, and the library. The church is not included in this tour. You can visit the church afterwards on your own. If you have any questions during this tour, please feel free to ask me. We are now in an area that starts out with the question, where do we actually of all religions live?
I first saw John without beard in 1949 when he came to AERE, the Atomic Energy, Harwell, where I had worked since 1947. After a very short time, Morgan, Worcestershire, to join the small group of Bill Walkinshaw to the theory of accelerators. During World War II, the radar establishment, TRE, was based there after a stay at Swanage. So I will finish a passage which he marked of special interest in some writings of Schrödinger. Whence come I and whither go I? That is the great unfathomable question, the same for every one of us. Science has no answer to it.
Thank you very much. It's certainly a great honour and a great pleasure for me to be able to pay my respects to John Bell at this meeting. I should say, when I first met John Bell, at least the first occasion which I had anything to do with him seriously, was when I was involved in organising a conference in Oxford, a quantum gravity conference. And how shocked and delighted we were when he gave us a talk telling us all sorts of things that we love to hear, so it's a great pleasure for me. Now, this talk has to do with, well, these are the major big theories of the 20th century, and at the bottom we have the problems, the major problems. Or I suppose for many people the problems would be these ones. Now, I think there are at least 3 reasons for believing that quantum gravity must be a non-standard quantum theory. One of them concerns this very question which I started with, which has to do with the singularities in general relativity. And if we look at the structure of these singularities, what do we expect? Well, we don't know what the whole universe is like, but what we expect from various considerations is that there's a Big Bang, certainly a singularity, and we expect to find singularities in black holes. Now, these may be all over the place, local ends to the universe, or it may be, if we have a closed universe, that the entire universe takes part in this great agglomeration of black hole singularities in the end.
What I want to do is to sketch an account of John Bell's upbringing in Belfast, his family influences, and his education. As well as giving a general description, I shall look to see if there may be anything in his upbringing that can explain, really in any way, the direction that his career took. I mean, naturally, I won't be trying to explain genius. There's certainly no point in trying to do that. But we may wonder, along with perhaps Professor Shimony earlier today, why his particular genius took him towards analysis of the structure and interpretation of quantum theory, an area of physics, we might say, when he took it up, there was really zero interest in that.
One of John Bell's major objections to quantum measurement might be overcome then by generalizing the definition to include processes in the big world. With this extended definition, quantum measurement is a universal property of physical systems. It's all around us and we wouldn't be here without it. Consequently, the dynamics of quantum measurement has universal significance, and so have its properties, like the weak non-locality of John Bell. Thank you.
With regard to my meeting with John Bell, I must say I have had a real problem as regards to EPR experiments. We have just started so-called quantum mechanically complete experiments in Stirling based on the theory of Fano and Meshack. So why then should I or my group be concerned with experiments questioning our basic research?
To use quantum mechanics to describe what's going on statistically in a deterministic world. And this might be, this might possibly be a way out of these difficulties that not only John Bell, but many others also encountered with quantum mechanics. And finally, I want to say that I hope that these ideas can emerge with string theory. Strings are also harmonic oscillators, so maybe we can try to use this gymnastics with string theory. I haven't done that, tried to do that yet. It's just a suggestion to do such things in string theory. I would have loved to discuss all these matters much more with John Bell, but he's not here anymore, much to all of grief, to discuss this. So I'd like to thank this, and I thank the organizers for the fun talk.
Please now return to your seat. Ensure that your hand baggage is either underneath the seat in front of you or in the overhead lockers. Please fold your table away now. Ensure the back of your seat is upright with the armrest down and that you've fastened your seat belt. If you have an onward connection at Heathrow and are already checked in and holding a seat number, could you please follow the signs for flight connections on arrival? If you have any questions on your transfer, please ask one of the crew. If you wish to travel into central London today, you may like to consider using the Heathrow
have here the following situations. Perhaps I should start with the experimental setup first, that you have some absorbing material in one beam. We call it stochastic absorption because each neutron has a chance to be absorbed or not, or a slow rotating chopper. The interesting feature is that at the same time when this interference disappears, in momentum space, a modulation occurs.
So we can start off thinking of a simple thing as a noiseless channel.
But of course, a channel can become noisy in various ways. By a channel, I just mean some way of delivering the quantum system from a place in which it's prepared to a place in which it is subsequently measured. So a noiseless channel is not disturbed en route. If the noise increases, we get to a region in which the noise can be combated and corrected by quantum error corrected codes. So it still functions reliably. And we get this larger region in which you cannot do that unless you have classical communication helping the error correction. And then finally you get this region out here where you can't send quantum information through it at all, but it still behaves in a somewhat quantum fashion because its ability to send in classical information is increased by prior attempts.
I must say that I never had the pleasure to interact with John Bell, so I cannot tell you anecdotes about my work with John Bell. It never happened. Nonetheless, his work had a serious effect on my research, and I would like to tell you very quickly today to what extent work on foundations of quantum mechanics, which seems to be very philosophical, turned to be applied and actually important from the point of view of data security. So the talk is roughly divided into two parts. The first part of the talk is about quantum cryptography and what it is. And the second part is a little bit more technical and basically says, it's supposed to show you where we go from now in our sort of understanding of quantum entanglement.
By 1978, however, we could already draw some fairly profound and startling conclusions. First, we defined realism, a philosophical view according to which external realities assume to exist and have definite properties, whether or not they're observed by someone. And from that definition, we could say that based on experiments in hand at the time we wrote this paper, that either one must totally abandon the realistic philosophy or dramatically revise our concept of space-time.
No way in hell.
Comment,
guys could
maybe I can help answer the question about
factor 10 to the 5th.
after
big issue had to do with
why
John Bell was
worst case.
pretty much the end of the talk. This was all
brought them together in a very nice conference.
From 1970 to 73, Fonda, Rimini, Weber, and myself, we were engaged in discussing and trying to derive the exponential decay law, which, as you know, is violated in quantum mechanics for large and small time. And then we worked out a model in which we were dealing with individual physical systems, and we were assuming that they were subjected at random time to projection operators, so the vector made a jump in the unstable state plan. So we were describing an unstable system which evolved in presence of an environment or whatever it is, which reduced it on the unstable method. The important fact is this, in my opinion, to have a description which has general validity. How can a proper chamber know whether I am studying a certain unstable particle or another one, and so reduce the system of EU? So we have made an analysis that we have made by resorting to potential scattering with just function as matrix form, and I proved that, and we have proved that if you assume that.
Second paper, signed by Bell, but published after he passed away, is a scientific biography of the main ideas of George Francis Fitzgerald, in which Bell insists very much, again, on the reality of the Lorentz contraction, by showing that this reality was also the main point of Fitzgerald. I had never the possibility to discuss about relativity with John Bell, because my interest in the field was born around 1992, 1993.
Something else that should be stressed is the point of view of Poincaré in relativistic physics.
So this is the challenges, and with these challenges in front of us, we cannot forget what John Bell said in 1963. There is no new physics without new projects. For the new projects, of vital importance are what John liked to call experimental checks. As we had this morning, I must tell you I knew nothing about John's life as a technologically minded, and I really understood today why he was so interested in these things, which I will now try to describe.
Anton, are you ready? Yes, sir. Or do you need another 5 minutes to prepare your transparent?
Yes, I need some time.
I could borrow some from people. We can interchange.
It is evident that one of the immediate consequences is that in physics we cannot talk about reality independent of what can be said about reality. Likewise, it does not make sense to reduce the task of physics to just making subjective statements, because any statements about the physical world must ultimately be subject to experiment. Therefore, this is now important, and I know that many disagree with that. Therefore, while in a classical worldview, reality is a primary concept prior to and independent of observation with all its properties, in this new view of quantum mechanics, the notions of reality and of information are on an equal footing. One implies the other, and neither one is sufficient to obtain a complete understanding of the world. Now, I would have loved to discuss these things with John Bell. Thank you very much.
there is no question. Thank you.
Oh, I'm a realist. And I think that idealism is a kind of, I think it's an artificial position which scientists fall into when they discuss the meaning of their subject and they find that they don't know what it means. I think that in actual daily practice, all scientists are realists. They believe the word is really there, that it is not a creation of their mind. They feel that there are things there to be discovered, not a world to be invented, but a world to be discovered. So I think that realism is a natural position for a scientist. And in this debate about the meaning of quantum mechanics, I do not know of any good arguments against realism.